we can start. So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and as probably most of you know, at the moment I'm the interim director of NITheCS. This afternoon, it's a real pleasure to introduce Regina Maphanga. Regina, I don't know, do I pronounce your first name correctly? I sort of pronounced it the Italian way.
Yeah, it's fine,
Yeah.
it's fine.
Okay, perfect, thank you. No, sorry, sometimes you need to be careful with these things. Yeah. So Regina is a principal researcher and research group leader at the CSIR and in the cluster on next generation enterprises and institutions. Yeah. Most importantly for us, she's also a NITheCS associate, and we are very proud to have her in our NITheCS family, if I can say so. Regina has a background in physics, and she is specialized in computational modeling of materials. Yeah? And today she will give us a talk with the title From Density Functional Theory to Machine Learning. Yeah, that has all the important buzzwords in the title. Yeah. So Regina, thank you very much for being with us today. We are really looking forward to listen to your talk. Yeah. And maybe while you start sharing your screen, I will quickly remind the participants to use the Q&A facility to ask questions, and Professor Ilya Sinaisky, who you also see at the top of your Zoom screen, will keep an eye on it and moderate the question session. And since we are not too many, if you raise your hands, we might have the time to give you the right to speak towards the end of the talk. Yeah. And sorry, and one last little announcement. Sorry, Regina. Sometimes I make a mental note of what I have to say and then I forget it. Yeah. After the talk, we will have a little virtual social event, and I will share the link in the chat, and the website where we are having the social event should open up automatically in your browser. Yeah. And that will give you the opportunity maybe even to chat a little bit informally with our speaker. So Regina, thank you very much. We are really looking forward to your talk. Thank you.
Okay, thank you so much, Prof Petruccione. Good evening, good afternoon, everybody. I would firstly like to thank NITheCS for giving me this opportunity to come and share the work that we do at the CSIR. And as my title suggests, I'll speak about the developments that have been happening over the years from density functional theory to where the future is leading us into machine learning. And as Prof said, these are the buzzwords that I think they will not just be buzzwords by the end of the presentation. I'm hoping that everybody would have learned something on what do we do. So I'm going to request to switch off my video because of the bandwidth, so that I don't get being cut as I present. So I'll request to switch off the video, then start with the presentation. I'm trying to find the icon for that, so sorry for that.
Your video is off, Regina.
Okay.
Oh, but the screen is no longer shared. I'm not sure what happened.
Okay, let me share the screen again.
Yeah, please.
Yes. Yes, the title of my presentation is From Density Functional Theory to Machine Learning, and this is the outline of my presentation. What I'll try to do in the next 45 minutes or so, I will give a brief motivation why we are doing this. This will be at a very high level without going into much details, and it will be covered in one slide. I'll I will then give a brief introduction on what is density functional theory, how does it work, and how do we apply it in material science. Then from there, I'll move to the discussion on materials designed by density functional theory. And design, in this case, I'm referring mainly to the functionality of materials, nothing beyond that. Then I will then move to materials designed by high throughput density functional theory. I'll try to explain briefly what is the high throughput density functional theory and why is it important. I will then move to the next section on materials designed by machine learning, and I will close my presentation by giving some overview and also some perception on the subject or the developments that are going on in the field. And on the right side of the screen, I have this picture that I liked so much because it shows how the science has evolved with time. And as we can see from the bit before or up to 1600, the science that was happening then, it was mainly experimental. So from 1600s up to 1950s is when the theory or theoretical science came into the picture, where we came across lots and lots of theories, which we are now implementing into computers and software to solve or to design these materials. So after the theories were developed until 1950s, then the so-called computational simulations, they were introduced. And they've been going on, but I think they became very famous in around they started to be known around 1970s. Then in the 80s is when that they became famous, or that's when people accepted them as part of science. But today, as we speak, there is a new version which we call the fourth paradigm, which it is mainly or simply defined as data-driven science. What happens in the fourth paradigm is that the data that is being generated over the years or since the beginning of science, it is now being looked at, or people are now saying, because we've got this lot of data, what are the decisions that we can make out of this data? And as I said, I'll try to take you through the different steps that has evolved as science was developing over the years. I'll not say much on the first paradigm. I will say a little bit on the second paradigm, where I introduced DFT, move to the third paradigm, where I'll share some of the work that we did and the work of others, where they used computer simulations to design materials, and end by the developments that are happening now in the fourth paradigm. And this is the motivation for my presentation. And in simple terms, the reason that we are doing this, the reason that I suggested moving from DFT to machine learning is simply to bridge the gap, or to close the so-called value of death in innovation. It has been established over the years that it takes decades for ideas to be commercialized, or for innovations to be commercialized. And I'm sure most people will agree to that. But recently, with the artificial intelligence, it is anticipated that this long time, which in the past was running up to 20 years, anything from 8 years to, or anything up to 20-25 years, it is anticipated that could be reduced to 3 to 5 years from the innovation stage up to the commercialization stage. They are saying that with machine learning, we should be able to reduce the time by at least 4 factors. And that's the motivation why we are trying to do this research that I'll be sharing with you today. And also, most importantly, I guess we can all agree that as part of human endeavor, science is a subject that is continuously being reshaped, as we have seen the evolution from the first paradigm to the fourth paradigm. And those are the reasons why we do the things that we are doing today, to keep up with time and also solve the challenges or the technological challenges that are out there. And moving to the introduction on density functional theory. So this theory was originally developed by Schrödinger, and it is based on quantum mechanics, and it's by its nature, it's a many-body problem, which means that because it's based on quantum mechanics, it's the particles that are involved here, they have wave, they have wave duality, meaning that to solve this, they depend on the wave functions, and we know that it is generally difficult to solve wave functions. So what happens with the density functional theory is that the many-body Schrödinger equation, it has been solved such that one can be able to calculate the ground state energy given on the right there. However, this has been mainly possible for systems with small number of electrons. So when the system becomes bigger or becomes larger, it is very difficult to solve the equation. And the ground state energy is given by the equation below the boxes, which is composed of your kinetic energy, your potential energy, the Hartree operator, and the exchange correlation energy. And as I said, that it can be done, and it is easier for systems with smaller electrons. But for systems that have more than, or that have larger number of electrons, it is difficult to solve that equation. That's when the Hohenberg, Kohn, and Sham theory was developed to systematically map the many-body problem into a single body problem. And what the theory or the theorems do is that instead of using the wave functions, the number of grid points are used. However, even though that can be solved, it is the challenge that is being brought upon is that if you were to do a simulation on that for 5 electron system, you will have a 10 by 10 by 10 grid, which will generate an information that is equivalent to 10 petabytes. So you can imagine the more complex the system is, how much information will be generated. So generally, this density functional theory is not able cannot be applied to systems that have large number of electrons. And around 1964, the Hohenberg and Kohn theorems, as I mentioned, that they were developed, but not much details were given. That's when Walter Kohn proposed that one can simulate materials properties, or one can calculate the ground state energy of the system, and that can be done by expressing the ground state energy as a function of the charge density, and it is given by this equation here. The reason that the ground state energy is expressed as a function of the charge density is because, unlike the wave function, the charge density is only 3 dimensions. It has only 3 dimensions, and it can be solved easier. And with the developments from the the theory by Walter Kohn, the different functionals were developed which are meant to really solve the exchange correlation energy based on the density. And the local density approximation was the first to be developed, and later the other functionals, because of the challenges that were encountered with the LDA. For example, it was overestimating the bond lengths of non-metal systems. It worked well for metallic system, but for the different types of materials, so it was overestimating the bond length and atomization. Then there is that the other approximations were developed, and I'll say a few things about them in the next slide. So we've got the GGA, the generalized gradient approximation, meta-generalized gradient approximation, and recently we have the so-called hybrid functionals. And this is what is called the Jacob's ladder in the field, where we have the different functionals. We start, as I said, the LDA was developed first, followed by GGA, meta-GGA, and the different types of hybrid functional. And we learned that as these functionals are developed, they were improving the accuracy of the calculations. And the LDA, it assumes that the exchange correlation energy density, it is at every position in space and is the same as a uniform electron gas. Then the GGA, it incorporates the gradients of the charge density at a point as well as the value, whereas the meta-GGA, it incorporates the Laplacian of the density, and the hybrid functionals, they incorporate the Hartree-Fock exchange energy. And this is a summary of the different functionals that are being applied in the field to solve different problems. And just to motivate or to show the effect that these functionals have on calculations, we've got an example of optimizing a simple system like water molecule. So this is what has been reported from the different functionals. You can see that the LDA, it overestimates the bond length as you compare with the experimental value there of 0.958, and also it, however, it underestimated the bond angle, the angle there. Then the GGA, it still overestimated the bond length and underestimated the angle, and we can see that as we proceed to the hybrid functionals are the ones that gave best results. As I mentioned, that they increase the accuracy of the simulations. And there are many properties that one can achieve or obtain from the density functional theory calculations, and I've shown some of them here. This is not everything, but these are the different properties that one can attain depending on what problem one intends to solve. For example, if you are interested in energetics, one can use DFT to get to calculate the free energies or energy of formation or heat of formations, all the different types of energies. One can look at the electrical properties, thermal properties, optical properties, depending on the interest and also the application that the application and the problem that one is intending to solve. And on the right here, I've got some example of the things that can be, or the models that one can generate. We've got the surfaces at the top. The first two lines are the surface where you can do your interfacial properties or your reaction mechanism properties. Then one can use these methods to simulate the nanostructures or nanoparticles, and also to agglomerate those nanoparticles and get some information out of them. And at the bottom there is a picture showing the mechanical change or the effect of mechanical stress or strain on the material, one can apply a certain stress to the material and observe how does that affect the system. Then moving to the applications, again, this is not a comprehensive list, but some, just to show some examples on where these density functional theory calculations can be applied. They have been applied successfully in many applications, such as in catalysts, in energy conversions and energy storage. They've been used in medical implants, drug delivery sensors, computer chips, light and electron emitting devices, to mention a few. And under the energy storage and conversion, they have been applied successfully on different technologies, for example, on battery supercapacitors, fuel cells, and so on. And in terms of the picture, the picture at the bottom there is showing mainly the complexity of the models that one could create and investigate using simulations, particularly in the biological field or in the medical implants or drug delivery. One can create as complex model as this and study their properties. It might not be necessarily DFT calculations, but computer simulations across the different levels. Then moving to the third part of my presentation, materials designed by DFT. Now that we have seen what DFT is capable of, what are the things that have been done. So I'll show a few examples on the work that have been done previously. And initially, when these computations were done, they were mainly just to understand the properties of existing materials. For example, if one is looking for tutorials of some code or software, they'll give an example on silicon as a material that one can train on, because those are some of the common or easy material that one could simulate. However, in the recent past, we've seen people moving from using computations just to understand existing materials, but to design new materials or to improve the properties of existing materials. And as I said, that the intention now is to move to machine learning, which is faster than the computations. So the computations have been there, they did very well, they accelerated the discovery compared to how the experiments were doing. However, they are still slower compared to machine learning. Then on the slide here, I'm showing some of the work that we did on simulating Brookite TiO2 for application in photovoltaic solar cells. What happened was that we took the model, we simulated the model, and we were able to calculate some properties. For example, here we've got our density of states, partial density of states for a 210 surface, where we are able to measure the band gap of the material, and from which we are able to understand how will the light absorb onto if this material is used in solar cells. And such information, when it is calculated, it is used as a descriptor for machine learning simulations, which I'll show later in my presentation. On this slide, I just wanted to show that we can design materials using DFT, calculate different properties, and those properties, they are later used as descriptors for machine learning. And this is that was an example on some of the work that we did. And on this example here is also another work that we did in collaboration with the experimentalists. What they did was that they synthesized the material in the laboratory, the nickel oxide material, nickel oxide nanoparticles in the laboratory. Then they wanted to use the material in energy storage. So they calculated certain properties, and what I'm showing here on the graph in the middle are the experimental optical properties that they've calculated for the systems. However, it was not clear to the experimental work what influence or what surface of the nanocluster influences the behavior. So what we did some simulations where we created the nanoclusters that we cut along the different surfaces. Then we calculated the optical properties as well, and we compared with we validated what they have done experimentally. And we found that the 111 surface was the one that was responsible for the behavior. Then also we did some work on water splitting, where we used simulations to predict the evolution reaction mechanisms and also the hydrogen evolution mechanisms for the materials that they were synthesized. And this was for the sodium ion sulfide. And the material has not been used as a catalyst in water splitting. So what we did was to do some simulations for them, particularly focusing on the reaction mechanism and predict some properties. For example, here we calculated the adsorption energy, which guided us on which of the surfaces will be more preferred. So we're able to predict the surface that will be more electrocatalytic compared to the others. Then the other work that we did is similar, is related to what I've just showed earlier on. And here what happened was that they are currently using palladium morph systems. So they synthesized the material in the laboratory, where they included the stannic oxide or SNO2, or an interface of palladium and SNO2, to see how will that affect the electrocatalytic behavior of these materials. And shown on the slide here are the models for the morph with just palladium, and the other one is a palladium interfaced with the tin dioxide. And we did the simulations again to see how will that impact the behavior of the material. So when you look at the adsorption energies, the calculated adsorption energies, you can see that the one without tin oxide was minus 2.44, whereas when you put tin oxide into the system, it gave an adsorption energy of minus 1.5706, which is more preferred compared to the minus 2.44. And what that meant was that when this tin oxide is introduced into the system, it improved the hydrogen oxidation reaction activity, while increasing the stability of the material. And this was matched against what is being found from the experiments, and there were agreements on that. So we used the simulations to validate what is being found experimental, and that's how the calculations were meant to be in the past. You have something that is being done in the laboratory, then you either validate or invalidate that. So that's what DFT has been done mainly. There hence a need to move to a situation where we, instead of validating what is done in the laboratory, we come up with new materials and ask the experimentalists to validate what we found computationally. And on the right here, I wanted to show that in addition to using these simulations to validate experimental work, they are also used in many ways to communicate science better. As you can see from the right there, we've got some of the models, or this particular work that we did, it featured as a feature cover for this journal. I think it's because of the capability of modeling or the visuals that one can get from models and relating them to our everyday life there. So this appeared as a feature cover for the journal there. Then in addition to what I've shown you, there are many studies that have been reported, so I'm not going to go through all of them, but there's this reference that I've listed here that shows a comprehensive list of different work where DFT and experiments were used to design new materials. And these are for different applications over the years. However, the reference might be a bit older, but there are lots of studies that have been done to show that these techniques can be combined together to bridge the gap on the value of death on the innovation curve. Then moving to the next slide on high throughput density functional theory. So what it means by high throughput density functional theory is that with a normal DFT, one will prepare each and every calculation at a time, then or run the calculation. Whereas with the high throughput DFT, one is able to prepare a lot of calculations, maybe thousands and hundreds of thousands of calculations all at the same time to calculate properties. And what it does is that it helps with a faster way of collecting data or collecting materials data, unlike the DFT calculations. So this is an automated way of an automated method of calculating materials property. So you can have 200,000 systems, then you prepare a workflow, then you submit the calculation, then that calculation will generate results, which when you are to do them manually or through the normal DFT, they will take a very long time. So it comes in between the DFT and machine learning. And its benefit is some of the benefits is that it accelerates materials data generation, and also it has been recently shown that on the high throughput density functional theory, machine learning algorithms can be implemented much easier compared to when you are doing your DFT calculations, because this machine learning, they depend on large amount of data. So when you have large data sets, then you can apply machine learning and try to make decisions out of that. And in the same way, it has been used previously to screen different types of materials. And this is an example on what is being reported for Li3FEPO4. What happened was that they used this high throughput computational screening calculations, and they came up with different new materials like those two that are listed there, the polyanion materials. And once those materials were discovered, they asked experimentalists to synthesize this material in the laboratory and measure the properties to compare with what they have found computationally. And there was an agreement between what the throughput calculations predicted with the experimental measurements, and these are the different morphologies of the system that were recommended, and these are the models that were generated. And this is just a classical example of how high throughput calculations can be used to quickly design new materials that can be synthesized in the laboratory and tested for different applications. And in the same way that I had the list for successful studies that were reported before. So these are the different work that have been reported for different applications. And what is important is that the search space here, this is the starting material that the different studies started with. And under the candidates, these are the new materials that were found after they did these high throughput calculations. And again, this was reported in this reference here. For more details, one can check the reference here. And you can see that the success rates for most of these calculations, they were higher. Then moving to the last part of my presentation on machine learning, and for those who are not in the field, just to simply define what is machine learning, is a branch of artificial intelligence pertaining to the creation of models that can effectively learn from the past data and make predictions and decisions when confronted with new situations. And it has been applied, or it has been used tremendously in many areas, such as pattern recognition, forecasting, bioinformatics, game theories, and other areas. It is only now that it is becoming to be applied in material science. And from the recent studies that have been going on, there is a promising future for this, and it is mainly defined based on performance, task, and experience. And just to link what I've presented on we have seen that, or we know that there are established computational tools, such as our or scientific tools that one can use, such as our experiments and the different computer simulation methods that have been used. However, there's this new field or emerging field on data-driven models and methods, and that's what people are interested in today. And this is how machine learning works. We've got a database or a materials data that could have been generated from experiments or computations, and we apply machine learning methods and algorithms to develop models or to predict the properties of some materials. And what is important is that there is a data that is being that have been generated over the years, and we need methods to manage, utilize, and even generate more data, particularly in the case of material science. And that's where machine learning plays a major role. And from the literature, it has been proven that this machine learning has already made impact in the field, particularly on predicting the properties of materials and also extracting information or knowledge via text mining. It has been used successfully to design and discover new materials, as shown in some examples. It has also been used to characterize materials. And closer to this presentation on computations, it has been used to develop interatomic potentials, particularly for classical simulations. And it has also been used to accelerate and improve ab initio simulations, particularly on the high throughput calculations. And however, there are challenges that are associated with applying this machine learning in material science. For example, among others, the data curation, the data that is there, sometimes it is not in the standard format that every other person who wants to use data, they can use it immediately. One needs to clean the data. So data curation in the field is one of the challenges. Then secondly, feature engineering, which I'll show in some of the examples that I'm going to present here. Then which model do you use, or which algorithm do you use? Then how do you fit the parameters, and how do you optimize the performance of the models? Also, there are challenges with model uncertainty and assessments. And finally, there is a challenge on final model predictions. The model that one prepares, how accurate are they? Then it has been applied, as I said, in machine learning has been applied in material science for some few years now, and there are different methods that are applied to solve different problems. However, there are two main methods, the supervised learning and the unsupervised learning, and these are the different methods that have been applied for undersupervised and unsupervised learning. And depending on what one intends to achieve, so this model choice will be based on that. Then if somebody wants to do regression, classification, clustering, probability estimation, or optimization, that depends on the final goal. And this is explained in the next slide here, that the process that one has to follow. Firstly, one needs to identify the problem. What is the problem that I'm solving? Then once you know the problem and where you want to go, then the first step will be to construct a sample. This will be the stage where you clean your data or you create your data. You also look at the feature selection, which of the features are important to the problem that I'm trying to solve. Well, then the next step will be to develop the model. Then lastly is to evaluate the model. And on the right is the same information that shows these different steps that one has to follow. So in simple terms, the machine learning workflow can be summarized as a goal plus data, which will be your step 0 and step 1, then the representation and learning algorithm and optimization. So if one has these 3 steps, I'll call them 3 steps because the other one is not necessarily machine learning, but part of the process. So once one has these 3 steps and understand the problem that they intend to solve, then it should be possible to apply this machine learning in material science. And these are some examples on the previous studies that have been done by different groups. Then in this in this work, they were predicting new structures. They had these combinations of materials or elements. So you can see on the y-axis there, we've got the SO4BO3, the different elements and the different transition metals on the x-axis. So what happens was that they developed a model to say that find any combination that has these different types of elements that are listed here. And what they found was that, or they calculated, they measured that from the value of the energy above hull, or energy above hull was the descriptor that they were using to predict their structures. And from the tables here, that they've got the first one where they have a lithium based, and the second picture they have sodium based, and on both cases it is noted that the CO3PO4 was the most stable, looking at the picture there. Then here I think they were doing the property prediction, where they took a group of structures where they say that from the periodic table, any element that is between 1 to 57 and 72 to 83, and it has this crystal structure types, the FCC, BCC, and HCP. Can you calculate the properties? Then they calculated the machine learning algorithms predicted or created the different combinations and calculated their bulk modulus as shown in the graph there. So in terms of structure prediction, these are the different types of materials that are found in literature where machine learning has been applied successfully to predict new structures. It has been applied in superhard materials, perovskites, binary alloys, phosphorus, and catalysts, and amorphous carbon materials. And I think this is similar to what I've just shown. Here they calculated the different properties, the heat of formation and the energy gap and the volume of the different systems. They used the database that contained about 240,000 DFT calculated in materials properties. And these are the measures that they use to measure the accuracy of their models. And you can see that the models are quite accurate to the R-squared value of over 90%. And this is an example of the work that we did. And as I mentioned, that there are different challenges that are there in applying machine learning in material science. So this is a new capability that we are still trying to build. I think it's about 2 years old from our research group. So we're still learning a lot from this. However, what we did was that the first thing that we did was to see if we could be able to develop a model, a machine learning model. And the approach that we took was that we took the information, the density functional theory information that is stored in this database called Materials Project. So we took the information from Materials Project database and selected the different lithium-ion battery materials. Then we did some feature engineering, and out of that, we wanted to calculate to predict the voltage of those lithium-ion battery materials by developing the machine learning model. So we tested the different algorithms shown in the slide. Here are the 3 different algorithms that we tested: the support vector machine, and the random forest, and the linear. And we can see that the linear method has performed very, very bad compared to the others. And as you can see from the picture there, so we were able to get an R squared or an R squared of over 90% for the random forest and support vector machine. And the reason could be that is because the linear model is meant to model very simple systems. So one can imagine that the materials, they are completely different and they might not be simply modeled with a linear algorithm. And these are some of the properties that we've calculated. We've calculated the different voltages, and this is the R squared of those voltages, the minimum, or the other one should be average and maximum voltage, sorry. So you can see from the values here that the support vector machine and the random forest and the deep neural network, they did well compared to the other two models. And also the other work that we did, which is a different work, was on predicting the formation energies for using the same data set. We wanted to predict the formation energy, because this property prediction, they depend strongly on the feature that one selects. So we tested the different models, and these were the top performing models compared to the others, the models on the x-axis, and this is as per the measured coefficient of determination. We can see that we found that the CatBoost model was the best performing model compared to the others. And the reason that we started with the formation energies, because the formation energy it's mainly it depends on the constituent elements of the materials, and for many elements the information is there is only for complex systems that some information is not there. So we will see in the next slide some of the properties that, or the parameters that we used as our features into the model. So we used these features appear on the first graph on the left, and we found that the electronegativity, the polyvalence, average valence D, and the number of valence electrons were the most important features for the formation energy. And why is it important to start with to perform feature engineering? It has a huge impact on the results that one get. And the other reason for doing that is because if that is not done well, there could be challenges with the overfitting. There could be problems with the performance of the model, and also the time that it takes to train the model could be longer if the features are not well chosen. So we did an exercise on selecting the features that are important to our calculation. So there were about 157 features in the database. So these were the top features that were impacting the performance of the model. And there are different ways of going or assessing or selecting features, different methods of doing that. We've got the so-called univariate, recursive, and tree-based feature selection methods. And these are the models that from the CatBoost model. This is the initial model that we got. Then we went further on to try and improve the model that we generated. So initially we got an R squared of 0.86, which when we played around with the hyperparameter. When we tuned the hyperparameters, that will be your number of trees, maximum depth, L2 regularization, baking temperature. We're able to improve the performance from 0.860 to 0.950. And these are the different formation energies for selected materials from the database. As you can see that the correlation is very good as it is observed from the R squared there. And from the literature, there are a number of studies that have been done using machine learning for materials or materials design. And these are the different studies that are available out there. And for example, in this 2016 reference, they were able to create 4,500 new stable materials by taking a large database of materials data and apply machine learning to design or to design new materials by playing around with the combinations. And in summary, I would say that I'm hoping that I was able to show that successful application of computer simulations within materials research include accelerated and accurate predictions of different properties of materials. That could be your phase diagrams, crystal structures, properties. You can also do the interatomic potentials, structure property relationships, and mapping. We can map complex materials behavior to process variables. And we have also seen that machine learning can be the fastest of all and will play a major role in supporting experiments and computations by identifying the most promising region of chemical space prior to computation or theory. And there's also an ever-increasing amount of scientific data that invites all of us, theoreticians, computationists, and experimentalists to explore this data. And I think there are opportunities that are available in the field, particularly on applying machine learning to materials research. As I mentioned, that the data is there, but it is not structured such that it is readily available when one needs to use it. So people could invest in how do we curate this data such that it is useful. And also there are lots of materials problems that needs to be solved, and at this stage there are no formulae or methods to say that this is how we go about it. And also we can look at converting the materials data into the format that is readable by machine learning. Some of the information is still in the form of pictures, graphs, all pictures and graphs that cannot be necessarily be read. I know that there are studies on pattern recognition and other things, but that's area that it has not been fully exploited in material science. And we can look at developing the algorithms and most importantly, the theoretical frameworks for this machine learning research in material science. And I would like to thank all the people that contributed to some of the work that I've showed here. And most importantly, I would like to thank NITheCS for giving me an opportunity to come and present and share my work with you. And thank you so much for listening.
Regina, thank you so much for the very, very, very nice overview of density functional theory and machine learning for material discovery, for discovery of new materials. Thank you very much. That was really very nice. Ilya, would you like to guide us through the questions that we have already in the Q&A? And you may want to judge whether you want to allow people to ask the questions in person, but maybe we can start with the questions that we have and wait to see if somebody raises their hand. Yeah, thank you, Ilya.
Okay. Yes, we have questions from anonymous attendees, so I cannot give them the right to talk. And we have some question from the person who indicated themselves. So if Kosi would like to ask question directly, you're welcome to raise your hand and I can give you the right to talk. Okay, but in the meantime, let me go to the anonymous attendee questions. Okay, so the first question is that machine learning approaches are data intensive. How do you get around this for such experiments? And in the same question, it's probably related to the first part of your talk where you were talking about the hybrid kind of approaches. And by hybrid, you mean physics plus machine learning, which means physics informed models or just data-driven hybrids?
Okay, the first question on data availability of large data sets. Yes, I think that the question is valid, but as I've said that in many parts of the world, there's been a number of moves on trying to take this materials data and put it in such a way that is usable. There are a number of databases that have been developed over the years, and some of them, they've got over millions of data. The one that I used is called Materials Project, and it has over 2 million of data, DFT calculated materials properties. So it has over 2 million of data set. And the work that I did on the lithium-ion battery material, we were able to get over 4,000 data set, specifically for lithium-ion battery materials. So there are a number of them, it's just that I didn't mention them here. There's NOMAD, there's QMCD, there are a number of these initiatives on building data sets, particularly for material science. So if the person is interested, I could share more with the person, but there is data available. Yes, there's still work that needs to be done, as I mentioned in my conclusion, that we need more efforts into curating this data and make it more useful. The second question on hybrid
On
functions.
hybrids.
Yes, so it is not, it doesn't include the machine learning, it is only the DFT. So inside the DFT theories, they added some features that are meant to overcome the challenges. For example, in terms of the hybrid functional, they added this Hubbard parameter. So you've got your standard GGA and the Hubbard parameter into your approximation. So that's what we mean but that's what I meant by hybrid functional. So they are DFT based, not necessarily a combination of machine learning and DFT. So they are still purely DFT.
Okay, thank you.
Yes.
So let's go to the next question from anonymous attendee. And how do you deal with the biases that are introduced during the feature engineering?
Sorry?
How do you deal with the biases that are introduced during feature engineering?
As I mentioned, that this is still a fairly new work that we are doing. So there are different methods of overcoming that. For example, in our case, we use the so-called five-fold cross-validation. So we use that method to remove the biasness from our models.
Okay.
Yes.
And if the person who asked the question is unhappy with the answer or want to specify a little bit, because I'm also not 100% sure that I fully understand the question, but maybe really by doing the k-fold cross-validation, you can really walk around possible kind of the issues. Okay. Are there any direct physical implication of the metric that you used, i.e. higher R2 measure, etc.?
Are there?
Are
Sorry,
there any direct? Yes, I'm trying to.
yes.
Are there any direct physical implications of the metrics that you used? For example, a higher R2 measure and so on. So kind of like maybe, you know, what the anonymous attendee want to know. Is there any reason why you choose R2, and is there what does it mean for the physics of the system of which you consider?
Okay, is it on the theory, on the DFT, or on the machine learning part? They use different things.
No, this is already on the machine learning.
Okay,
yeah, because
okay.
in the machine.
What we did particularly on the model hyperparameter tuning, we had a range which we start, for example, the different quantities that I mentioned, what is it? Is it let me see, the minimum depth, the number of trees, the regularization. We had a range of for each of them. So what happened was that we developed a models or a code such that it tests the different values that we've put in that range. Then from that test, it will pick the one that gives the best results. So that's how we went about it. So we had the different, we had the ranges for all the different quantities or parameters that I mentioned. Then, for example, when we got an R squared of 0.86, we had the number of trees as 1,000. Then when we changed that number to, it was ranging from 100 to 1,000. So when we changed that number to range from 350 to 1,000, then the model changed. So the same with the other parameters.
Okay, thank you. And so now we've got two more questions from the Kosiketi, and I don't know whether the Kosiketi would like to ask them by himself or herself. I can allow to talk.
Yeah, I can see.
Hi.
Hello, can you hear me?
Yeah.
Yes.
Yes.
Okay, thank you for your presentation. So I would like to ask just two questions. So in your machine learning model construction for lithium-ion battery material, so what you did is like you took available material in material project, right?
Yes.
So what specific properties of this material did you consider first? And secondly, how did you represent this property as input of your machine learning model?
We consider the atomic constituents, that will be your electronegativity, all those things that I showed as a list of features. Then we use that information to predict the voltage. I do acknowledge that we didn't go deeper into looking specifically at the features that will contribute or that are meant to contribute to the voltage, because the first aim there was generally to develop a model, to have a code that can develop the different models. So once that model has been developed, the intention is to go deeper into understanding what specific features are important to predict the voltage.
Okay.
Yes.
So I am curious about how you represent this property as the input of your machine learning model.
I'm not sure how we had a mathematical model for that, where we had the average
Yeah,
The averages, the
what
sums.
Let me talk a bit. It's like what I want to know. Like, for instance, if you want to build a machine learning interatomic potential, you need to represent the inputs of your machine learning model as the atomic center symmetry functions, right? So yeah, is this kind of information I want to have for your machine learning model?
Okay, let me show you what I've inputted. I have that slide there. Let me show you. On this slide. So these are the, as I said, we use the atomic properties. So you see the things on the left here, the electronegativity, the polyvalence, valence, but d-valence, and so on and so on. The ready, the sum of the ready, the metallic, the average metallic valence, and all those.
Okay.
Yes.
Can I ask my second question?
Yes, yeah, you're welcome to ask your second question. Thank you.
Yes. You show a slide comparing a machine learning properties with a DFT as a regression curve. If you can go back to this slide.
This is one of them. I've got two of them. Which one?
I am not talking in the case of lithium battery. You talk in general for machine learning property prediction. I don't. Yeah, maybe this one.
I've got two of these.
Oh. Okay, so this is your machine learning model comparing to a DFT.
Yes.
What the slide I mean, I saw in the x-axis DFT and in the y-axis machine learning results. So I don't know if you can find this slide. Yeah, this one.
Information in it, yes.
Yes. Okay, I'm okay. Thank you.
Okay.
Okay, thank you very much. I do not see any other questions in the Q&A, and also nobody out of the participants are raising the hands.
Okay, then Ilya, thank you very much, Ilya. Then if there are no more urgent questions, it's my pleasant duty to thank our speaker again very much for a very nice talk. And I would like to thank the participants as well for joining us this afternoon, as usual. And if you would like to interact and network a little bit virtually, please follow the link that I posted in the chat, and we can meet there just now, just the time to leave Zoom and go in there. In a more informal virtual setting. Yeah, so if you're curious, or if you would like, if Regina joins us to chat with her on a more informal basis, please join us there just now. Yeah, so thank you very much. Otherwise, maybe let me just announce the mini school that starts tomorrow afternoon. It's our first ever mini school in mathematics. Yeah, it's an introduction to category theory, which has some strong implications for mathematics, computer science, logic, and physics as well. Yeah? So if you're curious, please join us tomorrow at 2. The Zoom link you find, either it's in your inbox because we sent it to you, or otherwise kindly go to the NITheCS website and you will find the announcement there. Okay, perfect. Then thank you very much. Sorry, I was asked to send the link again. Okay, I can do that, although it's still in the chat. Okay, sorry, just a second. I need to go and find it again. Sorry. but I think in the background of your browser, a window should have opened with that website. so now we try to make it as easy as possible. Okay, then thank you very much. Have a good evening, and hopefully we'll see a few of you just now in our social virtual space. Thank you very much. Have a good evening. Regina, thank you very much. It was lovely to have you with us this afternoon.
Thank you so much.
All
Bye.
the best and take care. Yeah, bye.
Thank you.